The bipolar junction transistor is a powerful semiconductor device, but it is inherently erratic. At the microscopic level, its operation relies on electrons and holes moving through a silicon lattice, a process highly sensitive to temperature changes and thermal vibration. A transistor cannot amplify an alternating current signal out of thin air. Before it can process any external data or audio, it requires a highly controlled, pre-existing electrical environment to operate. Engineers create this environment through a discipline called DC biasing. This involves applying specific, steady direct current voltages to the transistor's terminals to force the device into a stable, active state. This deliberate application of steady voltage establishes what is known as the quiescent point, or Q point. The Q point is the perfectly still, inactive baseline state of the transistor before any alternating signal is introduced. Mastering the transistor ultimately means taming this Q point. If an engineer can prevent the Q point from drifting due to heat or manufacturing flaws, an incoming signal can be cleanly and reliably amplified. This Q point is defined by two specific electrical parameters: the collector current flowing into the device and the collector emitter voltage dropped across it. This graph maps the collector current on the y-axis against the collector emitter voltage on the x-axis. The straight diagonal line represents the DC load line, which defines the transistor's safe operating limits, and the dot perfectly in the center is our anchored Q point. When an incoming AC signal is introduced, it rides on top of this established Q point. Because the Q point is centered, the signal has maximum room to swing up and down along the load line, producing a clean, linear amplification. However, if the transistor heats up, the Q point drifts upward along the load line. The top half of the sine wave hits the physical voltage limit of the circuit and flattens out entirely, a distortion known as saturation clipping. Conversely, if the Q point is biased too low, it drops toward the bottom right. The bottom half of the signal flattens against the axes, causing pad-off clipping. Without a perfectly anchored Q point, the AC signal will inevitably hit these nonlinear regions. When that happens, the integrity of the data or audio being transmitted is permanently destroyed. To lock down the Q point, engineers developed various circuit configurations. The absolute simplest method is known as fixed bias. This schematic shows a fixed bias circuit. It relies on a single resistor connecting the top positive supply rail directly to the base terminal of the transistor. The fatal flaw of this design is its strict dependence on the transistor's DC current gain, known as beta. Beta defines the ratio of collector current to base current. Beta varies wildly due to microscopic manufacturing tolerances. Because the circuit cannot adjust, the fixed bias Q point is highly unstable, rendering it unsuitable for precision amplifiers. Engineers introduced a topological leap, the collector feedback configuration. The base resistor disconnects from the supply rail and reconnects directly to the collector. This creates parallel negative feedback. A collector current spike drops the collector voltage, starving the base and pulling current back down. Backshifting a single connection, engineers introduced self-correction, turning a blindly rigid circuit into a reactive, stable system. For high-fidelity audio or critical power systems, even collector feedback lacks the necessary precision. These applications require a more robust stabilization method called emitter degeneration. This method places a new resistor on the bottom emitter branch, completing the Emitter-Bias Configuration. This addition creates a powerful form of series negative feedback that aggressively throttles the transistor if it begins to overheat. The primary drawback of this emitter-bias setup is its power requirement. It demands a cumbersome dual-polarity power supply, needing both positive and negative voltage rails. To resolve this power constraint, designers developed the voltage divider bias as the ultimate single supply alternative. This schematic illustrates the voltage divider bias. The parallel network of two resistors on the left side creates a potential divider, establishing a rock-solid base voltage that is almost entirely immune to fluctuations in the transistor's beta parameter. This four-resistor layout achieves maximum thermal stability with minimal power requirements, earning its title as the universal standard for discrete transistor circuit design. Once the Q point is locked down, engineers must decide where to inject the input signal and where to extract the output. This routing decision drastically changes the circuit's overall behavior. This matrix compares the three primary transistor configurations used to route signals: common emitter, common base, and common collector. The rows track voltage gain, input impedance, and output impedance. The common emitter acts as the workhorse amplifier for high voltage gain. Meanwhile, the common base serves as a specialized low-impedance tool for high-frequency radio applications. But the third configuration, the common collector, universally known as the emitter-follower, serves a completely different purpose. The emitter-follower presents a strange paradox. It has a voltage gain of exactly 1. This means it does not actually amplify voltage at all. The output voltage simply mirrors the input. Engineers utilize the emitter-follower as a high-impedance buffer, protecting delicate signal sources from the loading effects of high-current power stages. The highly stable voltage divider bias is perfect for printed circuit boards, where physical resistors cost pennies and space is plentiful. However, the engineering math changes completely inside integrated circuits, or microchips. In silicon design, physical space is the most valuable currency, making large resistors impractical. To replace the 4-resistor voltage divider in silicon, engineers use a completely different topology, the current mirror. This schematic illustrates a current mirror, consisting of 2 physically identical gate-linked transistors, M1 and M2. M1 is diode-connected, tying its drain directly to its gate to establish a reference voltage. Sharing this exact gate voltage forces M2 to perfectly mirror the output current. By abandoning space-consuming resistors and relying purely on the identical geometry of matched silicon, integrated circuit designers can establish perfect Q points on a microscopic scale. To understand why impedance buffering is mandatory in circuit design, we have to look at a real-world engineering problem. Imagine a scenario where an engineer has a highly sensitive common emitter amplifier. This delicate amplifier needs to drive a heavy, low-impedance 270-ohm load, and they are connected directly by a single wire. The low-impedance load is exceptionally greedy. It demands far more physical current than the delicate amplifier can provide on its own. This creates a mechanical failure. The load effectively shorts out the amplifier, pulling its voltage down and causing a massive drop in gain. Raw amplification is entirely useless if the circuit lacks the physical muscle to deliver the necessary current to its final destination. The solution to this impedance mismatch is to sever the direct connection. An emitter-follower stage is inserted between the amplifier and load. Its massive input impedance acts as a protective shield, preventing the load from drawing current away from the sensitive first stage. While the emitter-follower doesn't magnify voltage, it safely replicates it. Importantly, it supplies the heavy current the 270-ohm load demands. With the buffer in place, the intact signal travels out of the amplifier, through the buffer, and successfully powers the heavy load without distortion. This demonstrates the precise calculation required in every stage of analog engineering, from 4-resistor networks placed on a breadboard to microscopic current mirrors in a silicon die. Every biasing technique serves a single objective: establishing the quiet, still Q point necessary for alternating current signals to exist without distortion.